So quiz, got to put the name of my favorite student. Good old Anne. She's amazing. A skydiver is in free fall. Have I mentioned that I jumped out of an airplane? He has been falling long enough to hit terminal velocity, so he's no longer accelerating. That's probably going to be important. I might, if it was a test, underline that to make sure I don't forget that. Which of the following statements are true? There are no forces acting on the skydiver since he's not accelerating. True or false? Oh, what are the forces acting on him? You might be considering getting the obvious one. Gravity and what else must be there if he's not accelerating? I guess air resistance or air friction or something's pushing him up. So, false. B, the magnitude of the gravitational force is equal to the magnitude of the force of air resistance. Yeah, true. Why did I say magnitude? Because their directions are what? Opposite. So I couldn't just say the forces are equal. Technically, they're equal, but opposite. So magnitude. True. The net force on the skydiver is 0. Absolutely true, because that's why he's no longer accelerating. I needed to get one more answer because I want to make each one of these, well, it's worth 2 marks, 4 answers, so half mark for each of these, and I couldn't think of anything clever. I wrote skydiver is slowing down. Obviously false, otherwise he'd be accelerating. So give yourself a score out of 2 there, half mark for each one. Ooh, a many-body problem right away. It says, find the acceleration of the entire system. All right, I'm going to label my forces. So this is going to be M1G, normal force number 1, tension, M2G, normal force number 2, tension slowing it down, applied force. Who's winning? I think vertically it's a tie because nothing is sinking into the ground like quicksand or lifting into the air like Superman. So I'm going to write a horizontal force equation. I think horizontally I'm going to say this. Winner minus loser plus winner equals, did I include more than one mass as I walked down this line? I did. Then I better include more than one mass times A. Oh, sorry, tension's canceling. So I'm going to get this. The acceleration is going to be the applied force divided by M1 plus M2. It's going to be 45 divided by, heck, I can add them together in my head, 25. Can I do this in my head? 45 divided by 25 is going to be the same as 9 divided by 5. 1.8? Yeah. Meters per second squared. How do I mark that? If you got the right answer, first of all, 2 out of 2. Otherwise, I'd probably do something like this. I suspect I would give you a half mark if I saw that, a half mark if I saw an expression for acceleration, a half mark for plugging in the numbers, and then a half mark for the answer. However, if you didn't put the units, I'm taking a half mark off. I'm a jerk about that in grade 12. Well, I've also tried to convince you, Jordan, as much as I hate memorizing stuff, memorizing units is well worth the bang for your buck because it really helps you figure out what goes where. Yes? You guys okay back there? Good. Thank you. Find the tension. Speaking of tension, find the tension between the 2 masses. That was a great segue, Mr. Dueck. You might have planned that. I wish I had. I think I will next class. I'm going to look at mass 1. Why? Because on mass 1, tension equals M1A. You could find it with mass 2. But in mass 1, tension is winning and there is no loser. Much nicer equation. Tension is going to be 10 times 1.8. Holy smokes, I can do this in my head. Is the answer 18 newtons? 1 mark for the equation, half mark for the numbers, half mark for the answer. I'm willing to bet the next question is this same diagram, but now let's include friction. Is that right? I think so. So it says, find the acceleration of the entire system in question. You know what? I'm going to go, there's mass 1, there's mass 2. There's mass 1, there's mass 2. I'll do a quick free body diagram here. What are the forces? I'm going to have M1G, normal force number 1, friction slowing it down, tension speeding it up. And I'm pretty sure tension is bigger because I'm pretty sure this is moving to the right. M2G, normal force 2. The applied force is 60. Friction number 2, I'll call this friction force number 1. Friction force number 2, and tension. By the way, why did I have to increase the force from 45 to 60? Because it turns out when I crunched the numbers with this new coefficient of friction, 45 wasn't enough to get it moving. Whoops. And rather than retype everything, I said, let's change the applied force. It's easier. Who's winning? So I think my equation is going to look like this. 60 minus friction force number 2 minus tension plus tension minus friction force number 1. That equals M1 plus M2 times A. Losing tension. A equals 60 minus friction is what times what? So this is going to be mu normal force number 1. Mu normal force, normal force number 2, mu normal force number 1, that's what friction force number 1 is, divided by M1 plus M2. Rats, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What's the same size as normal force number 2? M2G. I don't know the normal force. Oh, and by the way, as far as I know, okay, I'm going to take that. I was going to say, I don't think there is a way to calculate the normal force. I think there is a way, and I think you might learn it in third-year physics, university. But certainly in high school, I will never give you an equation to find the normal force. Bree, it's always going to be do a free body diagram, and you'll be able to figure out how big the normal force has to be by looking at why your object isn't sinking into the ground like quicksand or lifting into the air like Superman. So I don't know the normal force. Oh, but look. I know another force same size as the normal force, M1G. So this is going to become 60 minus, am I going to fit this all in? I don't know. You know what, Mr. Dueck? Do this. Yep. This is going to become 60 minus, what did I say mu was? 0.12. Mass 2. 15, was it? 9.8 minus 0.12. Mass 1. 9.8, all divided by 25. What did you get for an acceleration? Sorry? 1.2? Anybody else? So if you got that, you get 3 out of 3. Otherwise, how did I give out part marks? I can't remember how I gave out part marks for this one. Let's go look. Oh, wrong folder, Mr. Dueck. Vector Dynamics. Quiz 2, and I think I gave you, Quiz 1. I think you gave you Quiz 1 version 2, and holy smokes, I don't have an answer key for Quiz 1 version 2. I'll have to save one this time, apparently. That's sloppy. You know what? For 3 marks, I'd probably do something like this. I'd probably go 1 mark for that, 1 mark for that, half mark for that, and a half mark for the answer. But if you got the right answer, you get 3 out of 3. Speaking of, I bet you the next question I'm probably going to ask you to do is find tension. And before I do that, hint, 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 I also would have no problem doing this whole question backwards, giving you the tension, say find the acceleration. And once you know the acceleration, find mu, or find one of the masses. Or in other words, in this equation right here, I have 1, 2, mg, 3, 4. I've got about 5 different variables. I think all of them could be fair game depending on how I set this up. Yeah, find the tension between the 2 masses. I probably still use mass 1 because tension is winning. So it's going to look like this. tension minus friction force number 1 equals M1A. Tension is going to be M1A plus mu M1G. It's actually mu times the normal force. I don't know the normal force, oh, but look. I know the force same size as the normal force. It's going to be 10 times 1.2 plus 0.12 times 10 times 9.8. No idea what the answer is. 10 times 1.2 plus 0.12 times 10 times 9.8. Do you get 23.8? No? Yeah? And I'd take 24, but go to 3 sig figs. Be a little more accurate. Elevator. A 75 kilogram person is standing on an on a scale that reads the normal force in newtons. Oh, that's good. So I don't need to convert my answers to kilograms. I could just divide by 9.8. I don't need to. If the person and the scale are inside an elevator, find the scale reading in each case. Up. I think that means I have mg down. I think normal force is winning. I think I'm going to have normal force minus mg equals ma. I think I'm going to have normal force equals ma plus mg. How does that help me? Well, a scale reads the normal force. So even though this question said find the scale reading, what it's really saying is, hey, find what the normal force has to be, because that's what the scale is going to measure. It's going to be mass 75, A 1.6, mass 75, A 9.8. $855 newtons. What if it accelerates downwards at 1.2? Downwards, did I say? Why, that would mean that gravity was winning. That would mean that the normal force was losing. That would mean I'm going to have mg minus the normal force equals ma. I would probably then choose to plus the normal force to this side and minus ma to that side, and I would do that all in one fell swoop. So I would say the normal force equals mg minus ma, which is going to be 75 times 9.8 minus 75 times 1.25. Minus 75, no, good gosh, times 1.25. Did I type that in right? Let me double check. 75 times 9.8 minus 75 times 1.25, 641? No, yes, yes. Neve's nodding, so I think I'm right. I'm going to come back to part C. I want to do D first, because I can answer D intuitively, but I can also prove it from part B. Sam, what are we accelerating at in part D? Direction. Which means I would use this equation and put a 9.8 there. So I would have 75 times 9.8, take away 75 times 9.8. What happens when you take away the same thing from itself? You get what? And most of you intuitively say, oh, of course, you're in free fall, the scale would read 0. But we just proved it. I couldn't resist since that equation was sitting there staring at me. So I'm going to answer for 2 marks for part D, 0 newtons. Now let's come back, part C. Constant velocity, what does that mean? That means A is 0. Now, you might be tempted, because it's moving up, to let the normal force be the winner. It's going to be a tie, but just in case you didn't catch that, you might have said, hey, Dueck, I think it's going to be winner minus loser equals ma, but that's going to be a 0. You would have got, and like I said, you would have said, oh, it's a tie. It's going to be 75 times 9.8. You're going to get 735 newtons. and that's his apparent weight. Well, no, that's his weight. And in this case, his weight is also his apparent weight, because the normal force and mg happen to be the same here. It's when you're accelerating, you feel lighter or heavier, even though you're not really lighter or heavier. In terms of part marks, if you got the right answers, you get 2 out of 2. Otherwise, I usually go 1 mark for the equation, half mark for the rewrite, half mark for the answer. 1 mark for the equation, half mark for the rewrite, half mark for the answer. 1 mark for the equation, 1 mark for the answer, and here, I guess, 2 marks for the answer. Can you give yourself a nice clear score out of, is it out of 19? Is my math right? I hope. 2, 4, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, it is out of 19, yes? Give yourself a nice clear score out of 19, please. Make sure your name's on them, and then pass them inwards. So questions from the homework. Number 8, the system below is at rest. Find the normal force exerted by the table. I think I'm going to draw a good free body diagram first, to be quite honest. And I'm going to zoom in. Oop. The right-hand mass is going to be easy. I think the right-hand mass, it's m2g and tension. Yes? Which I guess means on the left-hand mass there must be tension. What else? Yep. Get the obvious one. You didn't get the obvious one first either, Mr. Dueck. Shut up. Okay, what else? Since it's sitting on a surface, there also has to be some kind of a normal force. There has to be. There has to be. Who's winning? Well, technically, since it's not accelerating, it's a what? It's a tie. But I'm going to let this be the winner only because as I move the normal force all the way around, that way it ends up a winner, and I kind of like what I'm looking for to be positive because I'll make less mistakes. Is that okay so far? So I think my equation is going to look like this. I think my equation is going to go, well, m2g minus tension, and then I'm going to have plus tension plus the normal force minus m1g equals, why did I put a 0 there?
A is 0.
Oh, it's not accelerating. A is 0, so it's going to be m1 plus m2 times a, but if a is 0, it's going to be m1 plus m2 times 0. You know what? Well, it's going to be 0. Tension cancels. What are we trying to get by itself? What are we trying to find? I think this question wants to find the normal force. Yeah. So you know what? I'm going to minus that over. I'm going to plus that over. I think the normal force is going to be positive m1g, take away m2g. Is that okay? Hey, by the way, what if these two masses were identical? What if, it would be barely touching the table. In fact, it would be touching the table so little that there would be no normal force. Wouldn't need one. Oh, because that would also mean you could lift it up and it would stay stable a couple of centimeters off the table. It would still be fine because you've got equilibrium, so two masses are the same. Right? That comes out of there. I think that's a reasonable conclusion I can make. That's, by the way, the other reason, Claire, I try and get you to do these algebraically is you can see a lot from this line that if there's all numbers there, you won't necessarily spot as easy. Is that okay? Any others? Go once, go twice? Good. So I got lots to teach today. Lesson 6. If you have this lesson 5 done, hand it in. If not, I'll still take it Monday. So today is where, in my mind, Physics 12 actually begins. Today is where, in my mind, we actually start doing some stuff that is completely new. We're going to take all that we've done with forces, and now we're finally going to say, hey, let's not be satisfied with flat ground. Let's look at ramps. They're much more interesting. The inclined plane is the fancy word for a ramp. So here's our first little thought experiment. A person is on a ramp standing on a Newton scale. and attached to a rope. As the angle of the ramp increases, what happens to the scale reading? No change, increases, or decreases? And convince me. I'm tempted to vote, but who thinks they can just figure this one out? So as the angle of the ramp increases, what's going to happen to the scale reading? No change, increases, or decreases? And convince me. Michael.
I think the scale reading will decrease because as you incline the rope, it takes on more of the force as the normal force.
The way I would answer something like this is I would probably look at the extremes. What do I mean by the extremes? When you're flat, that's the minimum incline. What's the maximum incline? Huh? Vertical, okay? I'm going to look at those two situations because I think, certainly, I've had plenty of experience on the flat. And then if I can figure out what it's going to be vertical, it must get there smoothly. It can't magically just suddenly change from one to the other. There must be a process. So I think what I would do is I would say, you know what? How about let's put a little angle theta right there where it says ramp angle. When theta equals 0, first of all, what does a scale measure? Normal force. So those is talking about scale reading. What it's really asking is what happens to which force? The normal force. When you're level, right? That was all of Physics 11 last year, just about. That's why, William, most kids started to think, oh, friction is mu mg. This is why I always barked at my students. I said, no, friction is mu times the normal force. And in grade 11, because we're keeping things level, the normal force is mg. What about when you're vertical?
Another rope.
Okay, all of your mg is going to be on the rope. What would the scale read?
0.
Nothing, because you're dangling in midair, right? How could you go from mg to 0 smoothly? You know what? I think you're slowly decreasing. You're decreasing. I don't know if it's decreasing in a nice straight line linearly or if it's a curve. I really don't care. It might be a good calculus-related rate question. Those either in calculus someday. But I'm pretty sure, therefore, it goes from maximum to 0. It must decrease. That would be a good way of handling it. I could probably handle it, Sam, also with a couple of good free body diagrams. In a couple of lessons, you'll actually be able to make up reasonable numbers and crunch the numbers. You'll actually know how to calculate the normal force on a slant. You could say, oh, I'll look at 20 degrees, 40 degrees, 60 degrees, and 90 degrees, and I'll show you that it's getting smaller. Fair enough. Same question. As the angle of the ramp increases, what happens to the tension in the rope? No change, increases or decreases, and convince me. And again, your hint is think about flat and vertical. Oh, yep.
I'd say it decreases because when you're just semi-down, the rope becomes dangling.
Yeah, no tension.
Yeah.
Sure.
When you're 90 degrees, the rope always becomes fully.
Yeah, you know what? I'm going to go like this. I totally agree with you. I'm going to go copy, paste, except I'm going to erase the normal force. I'm going to erase the mg. I'm going to erase the normal force. My argument's going to start out the same way. I'm going to look at 0 and 90. What did you tell me tension was when we're flat? Nothing. What about when we're vertical? mg. So it must be going from 0 to maximum. Must be increases. Must be. And what that suggests to me, Callum, is when we're solving for these on ramps, we're going to have to take theta into account. We're going to use some trig. Some trig. Components. Components. What the previous example shows is that for objects on a ramp, gravity is actually doing two things. It's partly pulling the object into the ramp and creating a Newton's third law normal force in the opposite direction. And it's partly pulling down the hill. The steeper you are, the more proportion of gravity is pulling it down the hill, the less is pulling it against the surface. The flatter, the more level you are, the more of gravity is pulling you into the surface, the less is pulling you down the hill. And that's why it's easier to walk up a shallow hill than it is to walk up a steep hill. What I wrote here was the force of gravity partly pulls the object onto a ramp, squeezes it, partly pulls the object down the ramp, or slides it. In terms of the other forces that act on the object of the ramp, there will be a normal force, which by definition is perpendicular to the surface. That's what the word normal means. And if there's rough, there will be friction. In fact, let's draw a free body diagram on this lovely big ramp right here. I would say to you, what are the forces acting on this block? And I would say, really, get the obvious one. Okay? Now, here's what we're going to do. We're going to break this up into parallel and perpendicular components. So I'm going to go to red, and I'm going to go dotted lines. I'm going to take that mg, and I'm going to break it up into 90 degrees into the surface and parallel down the slope, like that. And in fact, I'm going to call it, Jordan, mg, and the symbol for perpendicular is an upside down capital T. There's going to be a lovely right angle right there, which means thankfully the trig's going to be SOHCAHTOA. Woo-hoo. I'm going to call this one here mg, and the symbol for parallel down the ramp is 2 lines is parallel. 2 parallel lines is the symbol for parallel. See, I can't use P for perpendicular and P for parallel because, they both begin with P. Now, this couldn't be all, by the way, because if this was all, this would have to be sinking into the ramp like quicksand. Is it? Nope. There must be a normal force pointing this way, 90 degrees at an angle perpendicular to the ramp, and this normal force, try that again so that N looks normal, no pun intended. That's going to be the same size as mg perpendicular. Those two are equal. Now, if this block wasn't moving, right now this is impossible, because there is a component of gravity that's pulling it down the hill. If it's not moving, there must be friction acting up the hill, and friction must be the same size as that perpendicular component. Now, if it is accelerating, then we're not in equilibrium, and these don't have to be the same size up and down the ramp, although the normal force and the perpendicular component will almost always be the same size. We are going to break up ramps into parallel and perpendicular. Parallel and perpendicular. Example 3 says, draw a force diagram from object on a rough ramp that is sliding A, down the ramp, B, up the ramp. Okay. What are the forces acting on the first block? Get the obvious ones. Too slow. What are the forces acting on this first block? Get the obvious one. Straight down. Okay? And then put your pencils down for a second. There is a normal force like that, and you see it's tilted. It's 90, and this is why I've tried to tell you normal forces are perpendicular to the surface. So if your surface is tilted, your perpendicular is going to be tilted as well, 90 degrees to the surface. But I can tell you how big the normal force is. From here to here, didn't want to erase that. From here to here, pick your pencils up. This is mg perpendicular component. That's going to be the same length as the normal force. Do you know why I know? Because, Hakeem, is this block sinking into the ramp like quicksand? No. Is it lifting into the air like Superman? Then perpendicularly, my forces have to be identical. Opposite, but identical. Which way is this block sliding? Down the ramp? That's what's causing it to slide down the ramp. Does this question say there's friction?
Yeah.
Does this question suggest there's friction? Which way is this block sliding? Down. So which way is friction acting? But smaller than the parallel component of gravity, because if it was the same size or bigger, it couldn't move. How many blue forces did I draw on this diagram? 3. That's the free body diagram, those 3. If I ever say draw the free body diagram, Petra, please don't put the red component, the dotted line components on. Those don't go on there. But to do the math, we'll then break out the components afterwards to actually analyze this. But if I said, what are the forces acting on this block? 3 of them. Gravity down, a normal force that's preventing it from somehow sinking into the ramp, and if there's friction, in the opposite direction of the slide. B. What are the forces acting on B? Get the obvious one. What else? There is a normal force. Maybe I should have drawn that a little longer if I eyeball it. Let's see. From here to here, from here to here. Okay, maybe about like that-ish. Which way is this block sliding? Up. So which way is friction? Down the ramp. That's your free body diagram. Now, when we actually start to solve this, because normal force is nice, it's perpendicular, and friction is nice, it's parallel, we'll break gravity up into its perpendicular and parallel components. By the way, how many forces are pointing down the ramp now? Can you see it? 2. Gravity's pulling it down the ramp, and what else is slowing it down as it moves up the ramp? Friction. That's why you try sliding something uphill, it stops really, really fast, because there's 2 forces slowing you down. Compare with sliding something downhill, you got 1 force pulling you down, gravity, but you got friction kind of, I can't say pulling you up, slowing you up. So it's not going to slow down anywhere near as fast as this one. And again, the 3 blue forces are the free body diagram. If I ever say, please draw the free body diagram, and I will. That's what I want. But then if I say solve, you'll say, I better add some components and start crunching some numbers. So, example 4. Turn the page. Which of the following is the best force diagram for a mass that is at rest on a ramp? A or B? And convince me. William.
A, because if there wasn't a force of friction, there's no way it could be.
Okay. If B was right, if I imagine breaking that little force of gravity up into its components, certainly those 2 can cancel each other, but I have nothing canceling out that. That has to be accelerating. That must be accelerating down the hill. That can't possibly be in equilibrium. However, A, Oh, I've got a lovely little friction component to cancel out the parallel gravity component. So A, since we need friction up the hill to keep block stationary. Stationary, fancy word for standing still, at rest. Now, I haven't actually walked you through the trig yet. Alex, I've thought about this. What we're going to do to keep our lives easy, we're going to draw all of our free body diagrams identically. There's a method to my madness. This is one of the reasons I've always said get the obvious one. We're going to draw all of our free body diagrams identically, and we're going to prove once and only once how to find theta in your little drawn triangle, and then we'll always just put it in the same place. See, what you're going to get, what you're going to be given is this ramp angle here. They'll tell you the angle of the ramp, always. So I wrote here, in order to determine the size of the squeeze and slide components, we need to find out the angle in our triangle. So I would draw gravity down, and I would break it up into its perpendicular and its parallel components. We're going to do a proof because somehow, Petra, we need to find out where theta fits in this little triangle here. Does it fit in angle 3 or angle 4? We're going to do it once, and then we're going to say, let's always draw our triangles the same way so that we always know where it goes. You with me? Ready for a proof? Here we go. Ready, Petra? Angle 1 is how big? Yep. All right. Angle 2 is how big? Why can I say that angle 2 is 90 degrees take away theta? What does every triangle add to? 180. So this little tiny triangle here has to add to what, Cliff?
180.
How big? 90. These two have to add to? Have to add to 90. So that one's 90 minus theta. In other words, if that's 30, that's 60. If that's 20, that's 70. If that's theta, that's 90 minus theta. Do you see the Z? How big is angle 3? The same size as angle 2. Or is that okay? So how's that help? Look up. Do angle 2 and 90 and theta add to 180? Is this the same size as angle 2? Is this 90? Do these three add to 180? How big must angle 4 be? The same size as theta. In other words, Petra, that was the long argument to say, as long as you always, when you drop gravity, have I done my get the obvious one? Yes, drop gravity. As long as you always draw perpendicular first and then parallel, that angle and that angle will always be the same. Always be the same. And we're going to do it that way every time. On my answer keys, I'll always draw perpendicular first, then I'll draw parallel. Always. And if you don't grasp that proof, memorize it. This is one of the few times, memorize it. You will, because we're going to do it so often. In fact, turn the page. Let's actually crunch one. Example 6 says, find the acceleration of a 2 kilogram mass sliding down a frictionless 25-degree angle ramp. This is a job for a free body. Well, okay, technically I'm not drawing a free body diagram. Technically, I'm labeling the diagram with the forces. So what are the forces acting on this 2 kilogram? Get the obvious one. Gravity. By the way, Jordan, do you want to get this question wrong? Say no. If you want to get this question wrong, draw short, stumpy forces. If you want to get this question right, because you're going to be doing trig, trust me, you want nice big forces. Give yourself lots of room to make triangles. Another little tip of the trade, when you label mg, always put it on the same side as where the theta is. Since theta is on the left in this ramp, see the 25? Put it on the same side. What else? Hey, there is a normal force. Yep. Friction? No. Okay. If I said, William, hey, draw the free body diagram, that's it. Your free body diagram would look like this and like that. Okay? But now we want to solve. So what we're going to do is we are going to break gravity up into its perpendicular and parallel components. And look up, look up, look up, look up. How big? How big? 25 goes right there. That was the proof we did on the previous page. That's why, Claire, I said if you always draw perpendicular first, the ramp angle is going to go on the top of your triangle. Now, who's winning? And don't say mg. We're never going to use mg in our equation again. What force is pulling this down the ramp? Who's winning? mg parallel. Winner. Who's losing? It's a trick question. No one. mg what? Parallel, you said? William, my friend, here's the 25. Opposite, adjacent, or hypotenuse? Adjacent or hypotenuse, because mg is the one that I know. Which trig function, oh pray tell? Sine of 25 equals opposite over hypotenuse. Let's get mg parallel by the way, I know the m's would cancel. I'm not going to right now. Let's get the mg parallel by itself. How would I get the mg parallel by itself? What would I do with that mg? Times it. So if I hear you correctly, Hakeem, you're saying I can replace mg parallel with mg sine theta, sine 25 in this case, but sine theta in our generic case, which, Hakeem, I think means that I can rewrite this as, instead of mg parallel, what can I write in its place? Which trig function is mg parallel? Kelly? Again, which trig function is mg parallel? Sine. Again, which trig function is mg parallel? Sine. Will that always be the case as long as we draw that triangle the same way every time by always going perpendicular and then parallel? Yes. So for the longest time, I couldn't come up with a dumb, obvious way to remember this. Remember last unit I had my Vy is sine, and then last year I had a student who sat here whose name I've totally forgotten, and he said, hey, Mr. Dueck, 2 lines is sines. I said, that's not bad. So I bequeath to you parallel symbol, which is 2 lines, is sines. By the way, take a guess, which trig function are we going to use for the perpendicular component? Not sine, but cos, because those are the ones that go together. We'll prove it in a second. But here's what else. Yeah? Turns out, whether you're a 2 kilogram mass or a 200 kilogram mass, you're going to accelerate down the hill at the same rate. The mass cancels when we ignore friction. That's really important. How many of you have been on a roller coaster before? How many of you, before you got on the roller coaster, had to stand on a scale and weigh yourself, and then they had to carefully make sure certain people didn't sit next to certain people on the roller coaster? Did you never wonder why you don't have to do that? Because a roller coaster is a ramp, and as long as we ignore friction, what happens to the masses? Cancel. Oh, roller coasters do have friction, but do they grease those things down an awful lot? They're nearly frictionless. Right there. None of you ever wondered why you don't have to, like, why do we can just get on a ride? Shouldn't we have to, like, because we're doing some pretty extreme stuff, shouldn't they have to, like, weigh us and balance everything? Nope. Right there, because of that. Kind of cool. Oh, I guess A is going to be G sine 25, which is what? (9.8) sine 25. 4.14? Is that right? Units? Meters per second squared. Hey, Mr. Dueck, we didn't use the perpendicular, the normal force thing. Do you know when we're going to use the perpendicular? Hey, what force has the normal force in it? I heard it. Someone said it, or maybe they didn't. What force has the normal force in its equation?
Friction.
Friction. Did this question say no friction? Okay, we'll do one with friction in a little bit. We'll have to take into account the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, and it ain't no mg. Let's do another one. Oh, did I just find the acceleration? Okay. By the way, now that I know the acceleration, if I told you we started at rest, could you find like v final after a certain distance? Or if I told you how far, could you find how much time? Or if I told you how much time, could you find v final, or how far? All sorts of stuff opens up now. Okay. Turn the page. Example 7. It says, consider a mass sliding down a rough mu is 0.2, 35-degree ramp. A says, find the force of friction. B says, find the acceleration. Okay, what am I going to do first? Yeah, and again, I got to be fussy, William. Technically, because I'm not representing the mass with a dot in a separate location, I'm actually just labeling the forces, but we'll call it a free body diagram. I'm going to label the forces. Hey, William, what are the forces acting on this 5-kilogram block? Get the obvious one. Make it big. By the way, do you see the 35 degrees is on the right-hand side of mg? Put the mg there, trust me, because your triangle is going to be on the left-hand side. What else? Which way is this block sliding? Down. So which way is friction? That's the free body diagram, if I ever did ask you to draw that. I like friction because it's parallel to the ramp. I like the normal force because it's perpendicular. I don't like gravity. Let's break it up into its components. So we're going to break it up into perpendicular and parallel, where that's 90 degrees and look up. That one and that one are the same. Often because I can't fit the angle in there neatly, I'll just color a shade and color a shade, and those two are the same. For me to fit a 35 degrees in there is going to get messy and yucky and awkward. Okay. Which way is this block sliding? Down the hill. So think very carefully. Who's winning? Don't you dare say mg. Friction would mean it was sliding up the hill. Disagree. Huh? Ah, cliff. Winner. So down the ramp is going to be winner plus. Up the ramp is going to be loser minus. Any losers? Who? That equals MA. All right. Oh, I think we noticed that MG two lines ended up being MG sine. MG parallel ended up being MG sine. Yes. And I kind of gave the punchline away, Sam. I said perpendicular ends up being cos, but can I prove it to you? Sam, if this is my angle, opposite adjacent or hypotenuse. Yeah. And the mg is? Which trig function is a and h? Cos. Trust me, when you do the cross multiply, you'll end up with mg perpendicular ends up being mg cos. And you can derive it, but this is again is going to be one of the few times when I say, it's worth probably committing it to memory. Mg two-line sine, Mg parallel sine. Because now my equation becomes Mg two lines minus friction is what times what? Mu times the normal force. Sorry, mu times the normal force. That equals MA. I don't know the normal force. Oh, but look. I know another force the same size, exactly the same size as the normal force, and don't you dare say it's mg, because it ain't. Which is the Newton's third law reactive force that's actually causing the normal force? Hakeem. So if I hear you correctly, and I think I do, you're saying this is going to be mg parallel minus, don't forget the mu, common mistake, mg perpendicular, that equals MA. Is that what you're saying? And what can I replace mg parallel with? What's the angle? 35 minus mu. What can I replace mg perpendicular with? Cos. Oh, even with friction, is there an m in that term? Is there an m in that term? Is there an m in that term? Elijah, have you been on a roller coaster before? Did they make you stand on a scale and weigh yourself before you get on? Really? I wonder why. So normally I'd say, how do I get the a by itself? And you'd all say, well, you divide by the m. Turns out the math cancels. I think a is going to be g sine 35 minus mu g cos 35. Let's write in the numbers. So a is going to be 9.8 sine 35 minus, what did I say mu was? I've scrolled down. 0.2, is that what I said? Yeah? Minus 0.2, 9.8 cos 35. (9.8 sine 35 minus 0.2 times 9.8 cos 35. Do you get an acceleration? By the way, what's the maximum this acceleration could be? Think about the steepest this ramp could be. What's the maximum this acceleration could be? 9.8 if you were in free fall. So if you get an answer bigger than 9.8, you've hit something wonky on your calculator, right? 4.02, yes? No, I put it back. It should be up there. It might be tricky to find. 4.02 meters per second squared. By the way, that's the answer to B, because B said find the acceleration. Yes? What did part A want me to find? Sorry, what? What part? Oh, I got room over here. Part A. Friction is what times what? Mu times the normal force. Oh, I don't know the normal force. But look. I know another force the same size as the normal force. Don't you dare say mg, because it ain't. What is the same size as the normal force? Mg perpendicular? Cool. Which is going to be mu. Mg perpendicular was what? Mg, which trig function? By the way, get your calculators out. Let's go back to Michael's very, very first answer at the beginning of this lesson. He argued that when the cliff was vertical, what did you say the normal force would be?
0.
So you're saying when theta is 90, should be 0? What is the cosine of 90? Do you get 0? Oh! Michael was right. We just proved it. Cosine of 90 is 0. Oh, and when did you say it was going to be maximum? When we were flat? Hey, what's the cosine of 0? 1? Oh, are you saying the cos would just vanish and become a 1 and the normal force is just plain old mg? Ah. Confirms what I suspected. Here, though, we're going to go mu. What was the mass? Because here the mass doesn't cancel. So this is going to be mu mg cos theta, which is going to be 0.2 times 5 times 9.8 cosine of 35. 0.2 times 5 times 9.8 cos 35. 8.03. Now, you'll notice I did B before A. You can actually calculate the force of friction and then plug it in actually on this line right here. I love the algebraic because I got to admit, Neve, my little math nerd heart does go pitter-pat when the masses cancel. I have to admit, I can't resist doing that. So I'll rarely actually calculate the force of friction. I'll do as much of it as I can algebraically and get a little nerdy smile because every time the masses cancel, I remember getting onto roller coasters and not stepping on a scale. And I just remember getting onto roller coasters, and those are good memories for me. If you haven't figured out, nuts about amusement park rides. Example. Is that okay? So friction would be 8.03 newtons. I found that as kind of an afterthought. And again, nothing new there in that the equation hasn't changed. It's mu times the normal force. We've just actually, Hakeem, given a generic equation for the normal force. Last year, the normal force was equal to mg. Actually, no, it was always equal to mg cos theta. But last year, what was theta? Always 0. So what was cos theta? 1. So it never showed up. Right? Cool. Next one. How far am I going to get today here? Am I going to finish this? 2 more. It's going to be close. It's going to be close. It's going to be close. A 7.5 kilogram block remains motionless. Ooh, that's important. If you're motionless, what can you tell me about your acceleration? Sorry? So when I go winner minus loser, what can you tell me the answer is going to be? It's going to be a tie. It's going to be winner minus loser equals 0, which probably actually is going to make the question easier, I suspect. Let's see. Oh, what do they want me to find here? Coefficient of friction. Here's my ramp. (21 degrees). Oh, by the way, you want to get this wrong? Jordan, do you want to get this wrong? If you want to get this wrong, draw a really small triangle. I see it all the time. Kids get it wrong. There's a reason why I'm drawing stuff really big and exaggerated. Here's the block. What are the forces acting on this block? Get the obvious one. Good old mg down. Is this block sinking into the ramp like quicksand? No. Is it flying into the air like Superman? No. Then there's a normal force always perpendicular to the ramp, so it's going to be at an angle. Yoink. What else? Friction acting which way? Up the ramp, right? Gotta be up, not straight up the ramp. Like friction. And by the way, I'm pretty sure if I was being really, really, really fussy, and I won't be, but I'm pretty sure, Michael, that the length of the parallel and the length of the friction should be identical. Why? It's a tie. I won't be that fussy, but for what it's worth. There's my free body diagram. Now I'm going to go components. So I'm going to have mg, here's the perpendicular portion to the ramp. Mg, he's the parallel portion to the ramp. There's my angle. There's my angle. Adjacent, hypotenuse, no, opposite, hypotenuse. Or you may remember that two lines is sine and the other one's cos. Who's winning? It's a tie. But you know what? Let's let downhill be the winner, because that's the way it kind of wants to go. So which force is winning? Don't you dare say mg, because it ain't. Mg parallel. Who's losing? Put your pencils down. I could say, Sam, friction is the loser, but because it's not accelerating, what did we say the answer works out to? So would you just plus the friction over to the other side? Hey, pick your pencils up and just do this. Because that's the equation you'd end up with, yeah? Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? G perpendicular. Mg parallel, mu mg perpendicular. Hey, what was our substitution for mg parallel? What did we say that two lines were the same as? Don't forget the mg though, right? Sometimes I'll just see kids, they just write sine. No, it's mg sine. So it's going to be mg sine theta equals mu. Well, if two lines is sine, which one was perpendicular? Cos. Manisha, what were they asking me to find here? What symbol is the coefficient of friction here? Curtis, redeem yourself. Mu, right? Oh, can I do that? And actually, it's even weirder. Look up. What? Hakeem, are you saying I can even do that? Well, that's a little strange. How would I get the mu by itself? So you're saying that the coefficient of friction, the minimum, could be more, but the minimum coefficient of friction, so it's going to be sine 21 divided by cos 21. Did you guys in Math 11 in pre-calc learn what sine over cosine actually is? Tangent. It's actually turns out this is tangent sort of shows up here. I never bothered writing it as tangent, but for what it's worth, sine over cosine is tangent. You may be wondering, hey, how come we hardly ever use tangent in the component-y stuff? Well, it shows up once in a while. Anyways, what is sine 21 divided by cos 21? 0.38? 4? Units. What? Oh, mu is unitless. Now, Hakeem, what did you notice canceled that was kind of strange? Here's what this is saying. If you had Star Trek magic powers and you beamed this block, this whole setup, to the moon, it still wouldn't slide because G canceled. Or if you beamed it to Mars where gravity is different, still would slide. It'd still be in equilibrium. Or if you beamed it to Jupiter, still be in equilibrium. If you beamed it to the surface of the sun, assuming it didn't burn up, it would still be just happy. Friction could keep it there. It doesn't happen very often, but what we've just found is this particular system is universal. G canceled. Kind of cool ones. This is why I love doing the algebraic ones. That's kind of nerdly cool. By the way, why did I say minimum coefficient of friction? Could be bigger. Maybe it's really stuck, but you need at least that. Turn the page. I got 4 minutes left, 5 minutes left. I'm not going to finish example 8, so I'm going to but I want to give you some practice because this is where Physics 12 has begun. By the way, this is lesson 6. Lesson 7, I think, is called More Inclined Planes anyway, so I don't mind starting with example 8 as a continuation anyhow. But I want to give you some of these to try. I normally don't like giving homework on the weekend. Wait a minute, I'm not seeing you for like 5 days. So go trick-or-treating tomorrow night, have fun, but you can get it done. Do it tonight, do it on the weekend or whatever. So for now, number 1, two is good. 3 is good. Now 3 is asking you to do something with the acceleration. So part A says find the acceleration, and then B says find time to slide down and find speed at the bottom. So it's some nice applications. 5 is good. Eight is good. 9 is good, fairly yucky. 11, yeah, I'm giving you lots. These aren't all due Monday. You'll get more time to work on them. Give me a second here. Ooh, 15 is nasty. You know what? I'm going to leave that off. So what have I signed right now? 1, 2, 3, 5, 8, 9, 11. You know what? That's not that bad. If you have trouble with these, I'll happily talk about these Monday. Specifically, this one here is when you're sliding upwards. Be very careful. If you're sliding upwards, friction's pointing downwards. So is gravity. Your equation is going to be winner plus winner, no loser. Thank you for your patience, folks, but I wanted to make sure I really went step by step.